Hello everyone, this is Dr. Ian. For today, we're going to be working on special parts of circle involving chords. For today's lesson, we're going to be working on a special line in a circle called chords and how it differs from a secant line and a tangent line, and the theorems that we can formulate from chords in our circle. So by definition, a chord is a segment whose endpoints are on a circle, given by this diagram over here. So we are seeing a line segment PQ, which is inside our circle. And according to the definition of the chord, that the two endpoints that you are seeing in our circle is cut from this line segment PQ. And it's also related to arc PQ, which is this blue arc right here. So if we have a chord, its association to your circle is it produces an arc in this particular line segment. So notice that in a chord, we have two endpoints that is associated in our circle, and in a tangent line, the point of intersection only comes one time from a tangent line. So that's basically the difference between a chord and a tangent line. A chord is in the circle and the tangent line is on a circle. Now let's say we have another line segment AB. So this line segment AB is also considered a chord because its endpoint is in our circle, and the arc AB right here is associated with our chord that's formed from our line segment over here. So we have an arc AB and we also have chord AB every time we are working with chords on a circle. Now, secant line, if we extend our line segment PQ and draw a line through it, that is considered a secant line in geometry, and by definition, line PQ, which is a secant line, is a line that cuts any curve in at least two different points in our circle, which is pretty much the same as a chord because a chord is associated to our secant line because that line segment that is part of your secant line is what we call as the chord. So that's how those lines are associated with each other. And we know that in geometry, we need to know how to read, write, all those notations in our geometric figures so that we'll be able to understand the language that we are using in mathematics. So let's have the first theorem that we have with our chords and angle or central angles. And according to our first theorem, within a circle or in congruent circles, congruent central angles have congruent arcs. So there's so many congruency in that particular theorem, and it will make more sense if we have a diagram. So let's produce a circle O and central angles in this circle. So we know that the definition of a central angles are angles that has a vertex in the center of our circle. So this is an example of a central angle because its vertex O is our center. So this is our angle AOB or angle BOA, which is a central angle. And let's have another central angle that is congruent to AOB, which is COD. So if these two central angles are congruent, that means its associated arcs are also congruent, which means arc AB is congruent to arc CD. They have the same arc measure and same arc length. So that's the association between our central angle and our arcs. So this is our theorem in simple form. If central angle AOC is congruent to central angle COD, then arc AB is congruent to arc CD. And the converse of this theorem holds true as well. So that means if our arc AB is congruent to arc CD, then the central angle AOC is congruent to central angle COD. So that is the first theorem that we are going to be working on in a little while with respect to central angle and its arcs. And the second theorem that is also somewhat similar to our first theorem, according to this, within a circle or incongruent circles, congruent central angles have congruent chords. So this time it's not the arc that are congruent, but their chords, provided that the central angles are congruent within our circle or congruent circles. So that means if we have the same central angle, AOB, and central angle COD, if we connect point AB and point CD, which happens to be our chords in our circle, those chords are considered to be congruent or have the same length because of this property. And if we're going to write this out in notation form, that's why we need to know how to write our theorems. So according to the theorem, central angles have congruent chords in a similar circle or in a congruent circle. So let's start with central angle AOB. So if central angle AOB is congruent to central angle COD, then arc, or in this case, chord AB is congruent to chord CD. So that is our theorem and how you write it in symbol form when we are working with geometric theorem similar to this one. So the next one is it's in converse. So it's converse. It means that if their chords are congruent, then the central angles are also congruent. So if line segment AB is congruent to line segment CD, which happens to be our chord, then angle AOC is also congruent to COD. So that's our second theorem with regards to central angles and chord. Now let's work on congruent arcs and chord theorem. So in this particular theorem, within a circle or incongruent circles, congruent chords have congruent arcs. So if we have chords that have the same length, therefore their arcs are also going to be the same or congruent. So let's say we have chord AB and chord CD. If they are congruent, then their arcs, so arc AB, is also congruent to arc CD according to this theorem. So how are we going to write this theorem? So if our chords are congruent, and in this case, if AB is congruent to CD, then arc AB is also congruent to arc CD. So this is how we write this theorem according to its congruent chords and congruent arcs. And as I've mentioned, it's a must that we learned how to write our theorem using our symbol, because this is a good practice on how we develop our proving skills in geometry. And the converse of this proof is that if arc AB is congruent to arc CD, then chord AB is also congruent to chord CD. So this is our third theorem for the day with regard to arcs and chords in a circle. Now, let's have our last theorem, which is chords equidistant from the center are congruent from this particular theorem. So by definition, within a circle or incongruent circles, chords equidistant from the center or centers are congruent. So how are we going to illustrate that? So let's say we have a circle, and this is our circle, and let's say this is circle M. So let's say this line segment or chord PQ is equidistant. It may not look equidistant because I'm just drawing it freehand. So let's say this is SR. If these two chords have the same distance from each other and it forms a 90-degree angle, PQ and SR are congruent or the same length. So this is basically what this particular theorem is telling us, although the drawing is a little bit questionable. But if we have a proper diagram similar to this one, circle O, and we have chord AB, and we have chord CD, these two chords are equidistant from each other. That means they are forming a right angle within this particular relationship. Therefore, the measurement of chord AB is the same as the measurement of chord CD. So this is our last theorem about chords when they are equidistant from each other. And its converse is also true. That is, if chord AB is congruent to chord CD, then line segment OE is congruent to line segment OF. And OE and OF are the two lines that measures the equidistance or equal distances from those two chords in our circle. So let's use those theorems or some of those theorems to answer some problems involving circle. So let's say we have circle O, and in circle O, we need to measure the length or how long line segment RS is. So this is our line segment RS, and the information that we have chords that are equidistant from each other because they have the same length and they form a 90-degree angle. And we also have some of the measurements of line segment PR. And those line segments are PQ and QR that makes up PR in our diagram. So that means it's looking like we're going to be using this theorem to solve for the measurement of line segment RS. So we know that from this theorem, the line segments or the chords PR and RS are congruent since they are equidistant from the center of our circle. So that means since we know one of the measurements of the parts of PR, we can focus on that and measure it because we know that PQ is equal to 12.5, which is congruent to QR, so it's also 12.5. So adding them up, we have the measurement of PR, which is 25, which is significant because if we know the measurement of PR, from this theorem, we know that the chord RS is also congruent with chord PR. So that means the length of RS is equal to 25 units, similar to what we have for line segment PR. So this is how we use these theorems in proving some theorems in circles and chords and finding measurements, both lengths and arc measures of our circle depending on the problem that we are working on in geometry. So our Numberbender challenge for the day is for you to find the measurement of arc AB. So find the arc measure of AB using this diagram and the theorem that we had for today. So this is how we answer problems in geometry. So make sure that you know the difference between a tangent line, a secant line, how it's related to chords, and how the theorems that we are using in geometry will help us in answering some of the problems on circles in our lesson on circles, chords, and its arc length. This is Dr. E, and see you again next time. Bye!